Well, now we are going to discuss what happens when asteroids hit. And Rusty, you mentioned earlier actually that your colleagues on Apollo had a very good view of what happens when asteroids hit because we can see the surface of the moon. So can you contrast the two, the Earth and the moon?
Yeah, you fly around the moon and you see millions of asteroid craters, and that's really, in some sense, a better indicator than looking at the Earth in terms of understanding the shooting gallery, that we're part of as we go around the sun. People don't see that, of course, here on the Earth, and the reason partly is because Mother Earth protects us. Gaia, or Mother Earth, really takes care of us, both in the form of an atmosphere which really protects us from the smaller asteroids as they come in. Unless something is about the size of a 3-bedroom house, it's not going to make it to the ground. It'll burn up in the atmosphere. If it's fairly big, like 4 years ago at Chelyabinsk, that was about a 20-meter diameter object, and that one came in, didn't quite hurt anybody, didn't kill anybody. It blew up in the atmosphere and created a shock wave. But if it gets bigger than about a 3-bedroom house or so, then you're going to find serious damage on the ground. If it hits over water, it would have to be a good bit bigger to cause a tsunami. But the tsunamis are actually quite dangerous, and a large asteroid hitting in the ocean would create a lot of havoc around the borders of that water body. Water is very efficient at transmitting the energy of the impact long distances, even more than if it's an explosion in air. But there are the millions of craters that we see on the moon is the best indication to people that we're talking about a reality here.
Yeah. And actually, most of those craters, Patrick, were created, or a lot of them, during the late heavy bombardment. So in terms of the history, because if you look at the moon, you think it's remarkable that we've survived this long, actually, isn't it?
But we have a very short period compared to the age of the Earth. We need to remember. In fact, it's thanks to the craters on the moon that we could estimate that the current impact flux in the inner solar system is on average constant. Now we have the big basins, and thanks to the Apollo mission, which could date this basin, and there seems to have been an intensity in the impact flux about 3.9 billion years ago. We call that the late heavy bombardment because it didn't start at the origin of the solar system, or just when the Earth was formed, but it took a little time, about 700 million years, before suddenly there was a spike in the impact flux, which made these lunar basins. And therefore, it was difficult to understand how this could happen. It turns out that these are people in my team in Nice who generated the model, which is now the mostly recognized, which explains the LHB. It's called the Nice model, which if you read in English would be the nice model, so necessarily it's correct. And basically it explains the architecture, the current architecture of the solar system. So we reproduce, it explains why we have these asteroids sharing the same orbit of Jupiter. It explains also the small elongation of the orbit of Jupiter and Saturn. And it explains the late heavy bombardment. And the reason is that when the solar system formed and the giant planets were formed, they were surrounded by a disk of planets behind, which are now the Kuiper belt, the cometary belt. And the perturbation of this protoplanetary disk on the planet themselves took about 700 million years to build up. And that put the planet in a very unstable zone, which made them migrate. And by migrating, a lot of material went into the solar system, in the inner solar system, and generated this spike in the impact flux. But afterwards, once that was done, of course, the solar system became stable, and we entered the current era where we have all these small craters on the moon that tell us that we have a constant generation of near-Earth asteroids and impactor. The interesting thing is that most of them come from the main belt, the main asteroid belt. They have an average lifetime of a few million years. So you would say, how can it be that they live short before ending into the sun or a planet, and still we have a constant rate since 3.9 billion years? Well, it's because meantime in the main belt you have collision fragments which are created, enter in unstable zone, and they are sent to the Earth crossing zone. So while some of them evolve in the Earth crossing zone and then die, Some of them are generated again in the main belt, and we have this mechanism of death and natality which compensates.
Julia, given that these asteroids are flying around the solar system and crossing the Earth's orbit, have we seen any hit planets other than the Earth?
Well, we did. We were so lucky to see the comet Shoemaker-Levy 9 impacting on Jupiter, actually, back in 1994, I think. And that was an extraordinary experience. We were actually watching an impact live, I mean, while it was happening. And we also see some impact flashes on the moon. And after the impacts, after these flashes, we can actually see new and fresh craters on the surface of the moon. So we are watching them constantly.
And that was a large impact. That was a large object, wasn't it? Can you give us some sense?
I think it was already broken into pieces before impacting. Correct me if I'm wrong. So each of the pieces was about 4 kilometers, from 2 to 4 kilometers. So that was a big one.
But they made scars bigger than the Earth when they hit Jupiter.
Yeah.
I mean, incredible energy.
So in terms of the Earth, just to set the scene, if a 4-kilometer diameter comet hit the Earth, what are we talking about there?
Yeah, that's the equivalent of a dinosaur killer.
Yeah.
Because
Right.
the comets generally are
Control-Alt-Delete.
traveling fast.
Control-Alt-Delete.
Yeah, absolutely. Reset.
There will be a lot of boo-boo.
Yeah.
It may not be an extinction event, but it would wipe out civilization as we know it.
For sure.
Well, I mean, Rusty mentioned actually that to an extent our atmosphere protects us, certainly from the smaller ones. What do we know precisely about the impacts deflecting off the atmosphere, the angles, the modelling of the atmosphere? Do we know a lot about that?
Well, I spent a lot of time modeling that, and I've modeled the Tunguska event, the 1908 event that was on June 30th, 109 years ago today, and also the Chelyabinsk event that happened in 2013 that was captured on many dashboard and phone cameras, very well documented. And it turns out to be a very complex process. And in order to make a predictive model, you really have to know the details of the strength and the density of the impacting object. And of course, we didn't know anything about those. We didn't know they even existed until they hit the atmosphere. So we can infer something about how strong they were and how dense they were after the fact. But making a prediction, unless it's extremely well characterized, perhaps even with a rendezvous mission, beyond just Earth-based telescopic characterization, we're really not going to know at what altitude it explodes, and in some cases whether or not it'll even reach the ground.
But you can calculate that, given you know the orbit and the form of the object.
You can calculate where it would hit the ground if the atmosphere didn't exist. But for the smallish asteroids, the Tunguska size, which we think was 40 or 50 meters, or the Chelyabinsk size, which was about 20 meters, a little less than 20 meters, we really don't know how deep it would get before it explodes, because we didn't even know the shape of those. And without that information, we really don't know how long it would hold together until the pressure builds up. And the pressure may actually cause it to stay together longer than, if it's in one orientation versus another orientation, where it may start to fall apart and ablate and then explode.
I think one thing which is important is to realize that these processes are very complex and they are in extreme regime. So it's very difficult. We cannot reproduce in the lab the entry in the atmosphere of an object. And in fact, I'm doing the impact simulation of impact and crater formation. Mark is among the only ones who is able to do the entry in the atmosphere. So that's why we need this kind of expertise, because there are not that many people that do this kind of job. For the impact process, fortunately, we have bomb experiments that help us to calibrate the models, at least on Earth. We hope the IDA mission will fly so that we can calibrate with a real impact on an asteroid. And this turned out to be also important because the way we estimate the age of surfaces in the solar system is by counting the craters and estimating the impact flux that generated these craters. But in order to get an age from that, you need a relation between the size of the impactor and the size of the crater. And this relies on our understanding of this physics. And the same, if you want to know now for the risk whether you have a 30-meter objects coming out of you, what do you do? Whether it will hit the ground or what will be the effect in the atmosphere, you need this kind of modeling, and we can only rely on them. So that's why I push for continuing this kind of job. It's very important.